Good morning, class. We are on rocket activity number 3, plunger force. So what we're going to be doing is we're going to be testing different forces given to the rockets to see if that makes a difference. I think most of you know what's going to happen, but we're still going to go through the process and collect our data. Because it's one thing, even if we do know the answer, to say that it might be more or less, but it's another thing in science, and that's what we always do in science, is we need data as evidence. So we have to have data. If we can't do an experiment where we don't collect data, then we're just kind of wasting some time. So we need to find measurable data when we conduct experiments to prove our problem or to find the solution. So in this particular one, we are going to use plunger force, and we are going to try the different forces of the plunger on the rocket launcher. Unless you're doing a paper rocket, then you'd use your air and try different forces there. So the vocabulary, make sure that you complete the vocabulary definitions and write them down. We will probably have a vocabulary quiz at the end of this unit. So let's start off. Let's start off with this very first question. This very first question is kind of interesting because, let me see if I can get it all in there. Because what it's doing is it's sharing some different rockets. Now, in this one, this is just kind of a fun activity to compare many different types. Draw a line connecting the boxes with the rocket you think it best describes. So if on here, if I'm looking, each of these have different styles, they have different sizes, they have different shapes. So which one, just out of your own hypothesis and the things that you've tested so far or that you've witnessed through observations, which rocket would you think is the fastest? So make your best guess. You can write the letter here. You can draw a line to the ones that you think it is. Uh, Part B, which rocket can travel the longest distance? So which one do you think would be the best at traveling long distances? Number C, which rocket can carry the largest load? So which one would be that? Which rocket is the most efficient and which rocket would be the most expensive? So this is just some different things to think about in rocket design and different things that engineers have to think about too, because we have different objectives, like if they're going to the moon, or if they're just going to the outer atmosphere to release a satellite, or maybe they're just sending a rocket up into the sky to measure the temperature of, I don't know. I'm just making some things up here. So go ahead and figure out your guesses and see you're not right or wrong unless you leave it blank. Then what we're going to be doing is plunger force. So we will be testing our rockets. Again, if you are creating a rocket, you have a chance to redesign your fins so that you can try a different one. But once you start testing and collecting data, you cannot change those fins again. You have to leave them the same. So we're going to build a rocket and our requirements. So we're going to construct the rocket based on your group's collaboration. Then you're going to build the rocket using the following guidelines. It needs to be 10-centimeter long straw. We need to have 2 to 5 congruent fins. That means same size, same shape on those fins. Use small pieces of tape to attach. The nose cone, we're going to go back to 1 gram, and those that did the experiment know why we want to use 1 gram. So we're going to go back to 1 gram for the nose cone. If you're using clay or a ball of tape, back to 1 gram, which ends up being about a 1 centimeter square. Then draw what your rocket for this experiment is what it looks like, or what it's looking like so far, but what it looks like for the experiment. The experiment itself. So when we look at it, of all of the variables, the only variable we're changing this time is the plunger force. All of the other variables will reset to our standard. We're going to do the 1 gram nose cone. We're going to use the 10-centimeter straw, and we are going to use that 45-degree trajectory about. So whatever the 45-degree trajectory for this one. The plunger force will be in 3 measurements. Try to do one that's 5, try to double it, and then triple it for the last one. We've been doing 10 so far, so it'd be like half that, and then do 5 more than that. So that is our 3 different measurements for plunger force, so that we have them the same. Test them twice. If you want to do it 3 times, please do 3 times and then figure out the mean. Then on this particular one, the graph is a lot more empty than what it has been in the past. Make sure we have a title, we have our y-axis label, we have an x-axis label. Make sure you have an appropriate scale on both sides, and make sure that you're using as much of the graph as possible. Don't forget to put the best fit prediction line on there. It needs to be a smooth line so that you can make predictions based on other measurements. Your question, which straw rocket went farther? Then explain why it went farther. Use potential energy, kinetic energy, mass, and data collected. So when it says, when you're proving it with evidence, you should be using data. You should be telling me measurements. You should be giving me proof with numbers on why or how, or just explaining what happened when you tested it. So you should be including the data that you collected in your answer, and then explain why that happened. So explain it using these key vocabulary words and avoid the word it. Then you have questions at the end, communicate the conclusion, and going further questions. So another real world scenario to support your answer, okay? So please complete that packet, do the best you can, and please let me know if you have any questions. Thank you.